Okay, so let's go ahead and get started. Today we will be looking at nested quantifiers. Okay. Which is just a fancy way of saying that we're going to look at combinations of universal and existential quantifiers with respect to a mathematical statement. Make sure my camera adjusts. There it goes. Okay, so let's start with something like this. So okay, so try for a moment before I tell you, like, how would you read this? And you feel free to answer in the chat or say out loud what this says. Anybody? So universal quantifier, right? So what this says is for all x, for all y, x plus y is equal to y plus x. Okay. Now, if we're talking about real numbers here, this is the commutative law of real numbers. Okay. So, okay, what about this next one? All x, there exists. So how would you read that? Anybody?
For all x, there exists a y,
Such that?
such that x times y equals 0.
Right, so for all x, there exists a y such that x times y is equal to 0. So if we're dealing with real numbers, this is true, right? So for real numbers, these are both true statements. All right, so let's try one that's a little bit more involved. Okay, so okay, anyone want to take a shot at that?
All right, I'm gonna try it.
All right, good.
Is it for all x and for all y? And if x is less than 0 and y is bigger than 0, then x times y is less than 0?
Exactly. All right, so for all x and for all y, if x less than 0 and y greater than 0, then x times y is less than 0. Again, if we're dealing with real numbers here, this is a true statement. This is a tautology. Okay? So it's not so bad, right? It's just learning how to like read the symbols, and hopefully with the Zybooks, everyone's gotten familiar with ands, ors, if, then, for all, and there exists. Okay. So let's say let's try translating a English sentence into a logical statement. So let me say, okay, so the sum of two positive integers is positive. So there's a mathematical statement, and we wish to translate that into a logical expression. Okay. Anybody have any ideas as to what I should write as the translation? Well, we're considering any positive integers, right? So any integer. So there's actually several different ways that we can write this. So one way would be for all x, for all y, if x is greater than 0 and y is greater than 0, then x plus y is greater than 0. Okay? That's one way to write it. And this is assuming that our domain of interest is the integers, right? Now, if you wanted to be more specific, right? So this is like what you probably see in like a textbook, be like method, right? But another way to write this would be for all x that are integers, for all y that are integers, x greater than 0 and y greater than 0 implies x plus y is greater than 0. Now the only difference here between the first one and the second one is that we specify the domain explicitly here, so that the reader would know that that x and y both belong to the integers. Okay. And that's about it. There is a third way, but it's not. It wouldn't. You probably wouldn't see it in a textbook, but so for all x that are in z plus, for all y that are in z plus, x plus y is greater than 0. So z plus is the set of all positive integers. So in that case, you don't have to write the conditional. But all of these would be valid for translating that that sentence. Okay. Okay. So real quick, if you can, in the chat message board, just type yes if you've taken Cal 1. So as many of you respond as you can. So if you've had Calculus 1 or an equivalent course, type that in the message board and just send me yes that you have. Okay, we got a few yeses, current. All right, good. We have a lot of people currently taking Cal 1. Okay. So The following definition is one of the first definitions that you will encounter in Calculus 1. And what it says, this. So for all epsilon greater than 0, there exists delta greater than 0, such that the absolute value of x minus c less than delta implies the absolute value of f of x minus L is less than epsilon. So that is one of the fundamental definitions. I'm not telling you which one yet, but it is one of the fundamental definitions that you encounter in Cal 1. Can anyone tell me what this definition is referring to? Any guesses? So, if this is true, if this is a tautology, so f is a function, right? So this is just some function. C is a number, L is a number, X is a number, or X is a variable. This is f of x, right? So this is the same thing as saying the limit as x goes to c of f of x is equal to L. So that's the definition of the limit of a function as x approaches the number c. That thing right there. Now, even for those of you that have taken Cal 1 before, you probably don't really understand what exactly that means. Or if you do, it's not a very concrete understanding. When you see the absolute value of something, like the difference between two numbers in absolute value, what do you think of? Like, what is like the absolute value measuring when you take the difference of two numbers? Any guesses? Lots of silence. So whenever you have like the absolute value of the difference of two numbers, this right here is the distance from A to B. That's what the absolute value is telling me. So like the absolute value of 2 minus 6 is 4, right? So like it's like 1, 2, 3, 4, 5, 6, right? On the number line. Then the absolute value of 2 minus 6 is the absolute value of minus 4, which is just 4, right? So if you look at the distance between these, so if you start at 6, or we start at 2, so 1, 2, 3, 4. That's how far away 2 is from 6. 1, 2, 3, 4. That's how far away 2 is from 6. So this is just measuring a distance, right? Okay. So now that we understand that the absolute value measures a distance, what this is saying is that the distance between x and c, whenever that distance is less than some positive number delta, then the distance between the function and L, the limit, is less than epsilon. So now we have to look at the quantifiers, right? So for any positive epsilon, there exists an associated delta tied along with that epsilon. So you can even think of like that delta having a subscript epsilon, because it's, you pick that epsilon and then you get a delta that's associated with it. Okay? For any epsilon greater than 0, there exists another positive number, call it delta, such that when the distance between x and c is less than that delta, the distance between f and L is less than epsilon. If this is always true for any epsilon that you pick, then we say that the limit as x goes to c of f of x is L. There's a lot to unpack here. So I'd like to draw a picture to kind of to help with this process. So yeah. X is f of x. Okay, now suppose that there's some number like L right there, and then suppose there's a number here, call it C. Okay, and suppose that f converges to L as x approaches C. Okay, so if this is true, right, like if we're assuming this is true, then this definition has to be true, always. So pick an epsilon, pick any epsilon you want. Okay, so I'm going to pick an epsilon that's like that long. So then there's like L plus epsilon, there's L minus epsilon. Okay. Now what this definition says is that for all epsilon greater than 0, there exists a delta such that whenever x minus c is less than delta, so what we can do is say, let's look at c plus delta, and then c minus delta. So you agree with me that if you're in here anywhere, and if you're in that interval anywhere, you're within distance delta to c, correct? Like if I pick a point right there, you're going to be within delta to c, right? Because it's delta distance that way, and it's delta distance that way, right? And in here, if I pick any point in here, it's going to lie within epsilon of L. So, okay, this conditional has to always be true if we're assuming that this holds for the function. So let's pick an x in here. I don't know, like right here. I'll call that like x1. It's in there. So we look at it, x1 satisfies the hypothesis of this conditional. Its distance to c is less than delta. So then, because this is a tautology, if that's true, that better be true. So then f of x1 needs to be it has to land inside of here. For this statement to be true, it has to be within epsilon of L. Okay? Now, this is interesting because, well, we picked a kind of a big epsilon, right? But what if here's L again, here's C. What if we picked a really tiny epsilon, like minuscule, and then that's like plus or minus epsilon right there. Well, because this, we're assuming that this holds, any epsilon, there has to exist a delta. So that's like delta, so that's like C plus delta there, C minus delta there. There has to exist a delta for any epsilon we take, even a really small epsilon, right? So now, if I take something inside of here, we're guaranteed that, okay, that's true, so then this must be true because we're assuming this is tautology. So that means that this is like x, this is like x2 maybe or something like that, that we picked inside of there. The output has to be squeezed in there in that little epsilon ball around L. So, hopefully that kind of like helps with the understanding of the definition of a limit when you think of it in terms of the logical structure. For any epsilon we take, there has to exist a delta such that if we take an x close enough to C that's inside that delta ball, then the output of that will be inside the epsilon ball around L. Okay? Again, hopefully this like, helped a little bit with the understanding of the limiting process. Okay? Okay, so I think that's all I want to talk about with nested quantifiers. So I'm going to stop this recording.